Today we're going to talk about mental multiplication and division. A lot of the principles are the same as they were for mental addition and subtraction, just modified slightly to fit for multiplication and division. So if something isn't quite clear, you might want to go back and review that video. It might help clarify some of the principles. But I'm going to assume that you know what was covered in the addition and subtraction video and go from there. Okay. As you remember from the addition and subtraction video, one of our big goals is to make a number that ends with 0 or zeros. And so using this problem to do mental multiplication, we would end up using two principles. The first one would be the commutative principle. And that tells me that I can move numbers around without changing anything. So I'm going to rearrange the order of this problem. And then my associative principle tells me that I can group them in any way that I want. So I'm going to group it in a way that will give me a number that ends with zeros, in this case with 2 zeros. Now, when I do it, I end up with 46 times 100, and my answer, very simply, 4,600, or 4,600. So this principle is called compensation. Again, I'm not concerned that you know the names of what you're doing, but just that you can manipulate numbers to accomplish these things. But if you want to know the name of it, this is compensation. Compensation is looking for things that are already there that you can combine in a unique way in order to make a number that ends with a 0. The next principle for multiplication and mental multiplication and division is the substitution. And this one is going to employ the distributive property, a new property in multiplication and division that we did not have in addition and subtraction. But the distributive property lets me take this number apart and then multiply 21 times that whole thing, which really is saying I'm going to do 21 times 100, and then I'm going to do 21 times 3. My answer is going to be 2100 plus 63, which will give me 2163. Very easy to do that mentally. Wouldn't be quite as hard to try to keep all the carrying and regrouping and lining up numbers if you actually tried to do it out in your head. Okay? So again, my principle is to look for a way to take a number apart in order to have one of them end with zeros. Makes it easy to work with. This also works with a number that's a little bit under 10 or 100 or 1,000. For example, if I have 25 times 98, I can do the same thing. I can still work with this and get it to come out to 100. But this case, instead of adding something to the 100, since this is a little bit less than 100, I'm going to subtract. Then I'm going to do 25 times this. I'm going to get to 2,500 minus 50. All right? So whatever the sign is in here is what's going to be the sign in your final problem. And so I have 2,450 for my answer. Right? These are both substitution where you break it apart to two numbers added together or two numbers subtracted from one another. Compensation and substitution were both used in mental addition and subtraction as well. So they should be fairly comfortable. These two are a little different, but not completely different. We have equal products is the first one. And it's something like the equal differences that we did in addition and subtraction. But equal products, I'm going to do 22 times 18 for an example. Neither 22 nor 18 are easy to multiply by in your head. So I have to do something to them to get one of the numbers to turn into something I can multiply by easily. Often you want to get a one-digit number. That's a possibility. In this case, I'm going to get 22 to turn into 11. Okay? Now, before we go any further, let's talk about the property that's involved here. The property that's involved here is the property of identity, which says the identity property for multiplication is I can multiply anything times 1 without changing its value. Well, let's think for a minute. If I do 1/2 times 2, what do I get? I get 1. So if I do half of one number and 2 times the other number, I have multiplied the whole thing by 1, therefore I have not changed anything. All right? So that's the explanation for why we can do it, but let's go on now to how we can do it. So I'm going to, I already said, make my 22 become 11, which means I divided it by 2, so that means, therefore, I must multiply this by 2. And here I get to teach you a cute little trick for multiplying by 11. Any number you multiply by 11, you take the number and split it apart and add up the 2 pieces and put it in the middle. So 11 times 36 is 396. Very simple to do in your head. That would be one way of solving the equal products. I could do it the other way. I could divide this by 2 to get 9, which is pretty easy to multiply by, and multiply this by 2, which would be 44 times 9. Personally, not quite as easy, but that may work better for you. There's no one right and wrong way to do it, but you're doing opposite things. If you're multiplying this by 2, you're dividing this by 2. So you're just changing the proportions of them without changing the problem. Okay. So that's equal products. A very similar idea occurs in division, where we have equal quotients. What am I doing? Writing in D. Quotients. Okay? Now, the identity property works here as well. But since I'm dividing, I have to think, what divided by what equals what? Okay? What would have to be true of these two numbers? They'd have to be the same. So I either have to divide them both by 2, or divide them both by 3, or divide them both by 4, or whatever, because since it's a division problem, my numbers have to be the same in order to get to my identity property. Let's take a problem like 144 divided by 18. Okay. Now, neither one of them look like there's any real easy number with a trick, so let's go ahead and get this one to a number that is a single digit, which means I'm going to make that into 9. So I divide it by 2. If I divide this by 2, fairly easy to do in your head. Right? Now I have 72 divided by 9. Can I work that in my head? Yes. And my answer is 8. Okay? For those of you skeptics, 18 times 8, 64. 8 plus 6 is 14. So it does produce the same answer whether you do it with the regular number or a smaller, simpler number. Another one, we'll do 28. That was back on my equal products. Let me do 170, or 1700, yep, 1700, divided by 50. That wouldn't be too hard to do in my head, but I can make it easier to do in my head if I multiply this by 2 and multiply this by 2, and then dividing by 100, I can take out the zeros, and my answer is 34. So I can make either both numbers smaller or both numbers bigger, as long as I increase them by the same ratio. I haven't changed the problem. One last thing we want to look at, again, very similar to a concept we talked about in addition and subtraction, is partial products. This is not mental math, but this is another way that students sometimes do multiplication problems. Okay? We did partial sums in addition. So let's pick a problem. Let's do 35 times 42. Okay? In this case, I'm going to do each number on the bottom times each number on the top separately and write its answer. So I'm going to do 2 times 5 makes 10. Then I'm going to do 2 times 30, which makes 60. This 3, because of its position, is not a 3, but it's actually a 30 because it's in the tens column. This works really nicely to help the children understand place value. It also eliminates the need to move things over. Here I'm going to do 40 times 5, which is 200. And then I'm going to do 40 times 30, which is 1,200. Okay? I add up all my numbers, and I get my answer. And again, for skeptics, let's do it the traditional way. Proof that the number comes out the same. Carry, I get 7, 20, 40. Okay, so I got the same number no matter which way I wrote it.